If U is a subspace of Rn, there exists an orthogonal complement. This means a subspace that is orthogonal to U. We call this U perp. Perp meaning perpendicular. By definition, this is x, which is in Rn, such that x dot y equals 0, where y is any vector in U. On this grid, which is R2, what would be the orthogonal complement? It contains all vectors that are orthogonal to this subspace U, this line. That looks about right, as we see 90-degree angles. This is U perp. U perp is also a subspace of Rn. If U is the span of, let's say, x1 to xk, U perp would contain vectors x such that x dot all of these vectors is 0. Lastly, two interesting facts. The perp of the 0 vector, if we only start with the 0 vector, every single other vector is going to be perpendicular to it. So this would be Rn. If we go the opposite direction, if we start with all the vectors in all of Rn, the only vector that's going to be perpendicular to all of these vectors is the 0 vector. This leads into projection. If we have a subspace U that's in Rn, any vector, for example, if this is x, we could rewrite this vector as first projected on U. This would be proj, then U, meaning on U, of x, plus this vector, which would be perpendicular. This would be x minus the projection of x on U. Two interesting things. The projection of x on U would be the closest vector in U to the vector x, and this would be an element of U, our subspace, whereas x minus the projection of U would be included in U perp. If we think of this as a transformation, say the transformation of x is the projection of x on U, this is a linear transformation. The image of the transformation, or the entire space it reaches, is U, and the kernel of the transformation, all the vectors that go straight to the 0 vector, would be all the vectors in U perp. If we take any vector in U perp and we project it onto U, or subspace, we would get 0 as the dot product between all elements in these two spaces is 0. Lastly, we could note that the dimension of U plus the dimension of U perp is n, the entire domain, Rn, which is n-dimensional. Let's find the orthogonal basis of U, and then find the vector in U that is closest to this vector x. First of all, this basis clearly is not already orthogonal, as the dot product of each pair is not 0. Let's use the Gram-Schmidt algorithm. E1 is 1, 0, 1, 0. Then let's normalize this. This would be 1 over root 2, the norm, times the vector. E2 is x2 minus the portion already covered by n1. To find this, let's do x2 dot n1, which is 2 over root 2, minus 2 over root 2 times n1. This vector already has a norm of 1, so the norm is itself. It's already a unit vector. E3 would be x3 minus the portion covered by n1 and the portion covered by n2. x3 dot n1, which is 1 over root 2, and x3 dot n2. So we have 1 over root 2 n1 minus 1 n2. E3 will be 1/2, 1, 0, negative 1, 0. And we can normalize that. 1 over root 2, 1, 0, negative 1, 0. The vector in subspace U closest to x would be the projection of x on U. To find this, let's add together the portion of x covered by n1, n2, and n3. Let's compute these dot products. Firstly, we have 1 over root 2 times 2 minus 1. The next dot product is 0, so x is already completely orthogonal to n2. And lastly, we have 1 over root 2 times 2 plus 1. Now we can write our answer. And our final answer is 2, 0, negative 1, 0. If we were asked to write x in terms of a vector in U and a vector in U perp, we could compute this easily. X minus the projection of x on U would be a vector in U perp. And we could say that x is the sum of 2, 0, negative 1, 0, a vector in U, and 0, 0, 0, 3, a vector in U perp.